Welcome back everyone to another video in our FE Civil Preparation course. In this video, we are going to talk about stability of retaining structures. In our last videos, we learned the concepts of vertical and horizontal stresses on soil, and we learned how to calculate horizontal earth pressure on a retaining wall. Retaining walls are structures that we use to support an excavation site to prevent it from collapsing. There are multiple shapes of retaining walls. We have gravity retaining walls, which rely only on its weight in addition to the passive pressure to resist the soil pressure, and there are also cantilever retaining walls, which we rely on the wall weight in addition to the soil weight above the foundation to resist the soil pressure. First thing we need to learn before studying the stability calculations of a retaining wall is the failure mechanism of a retaining wall. Retaining walls could fail due to one of the following causes. First failure mechanism is called sliding failure, and in this failure, the soil pushes the retaining structure horizontally and it starts sliding. Second failure mechanism is called overturning failure, and in this failure, the soil causes the retaining structure to rotate around its toe, which causes overturning. Third failure mechanism is called bearing capacity failure, and in this failure, the stresses under the retaining structure exceeds the bearing capacity value due to its vertical load and differential moment. In this video, we are going to learn how to check each one of those failure mechanisms. First case here is going to be sliding check in case of gravity walls. The sliding force we have here is the soil active force, which is the soil pressure behind the wall, and we have learned how to calculate it in our last video. While the first resisting force is the soil passive pressure, which is the force due to the backfilling height behind the wall, and we have learned also how to calculate it in our last video. Second resisting force we have is the friction force, which is the force due to the wall weight, and it equals to the weight multiplied by the coefficient of friction between the concrete and the soil. And the coefficient of friction between concrete and soil is calculated as tan phi, where phi is the angle of friction between concrete and the soil. It is very important to remember that phi here is the angle of friction between the wall and the soil, not the internal angle of friction of the soil. And this phi value is normally given separately in the problem. And if it is not given, then the angle of friction between concrete and soil could be assumed to equal 2/3 of the internal angle of friction of the soil. Third, and the final resisting force, is the adhesion force, which is the adhesion force between the wall and the soil due to the cohesion of the soil. And the adhesive force exists only in case of cohesive soil, while in cohesionless soil it shall equal to 0. The adhesive force could be calculated using the formula, which is adhesive force equals to length of base multiplied by C, where C is the cohesion of the soil. After calculating the total driving forces and total resisting forces, the factor of safety is going to be calculated by dividing the resisting force over the sliding force. If the factor of safety is less than 1, it means that the retaining wall is not safe, and if the factor of safety is more than 1, or any given specific required value for the factor of safety, it means that the retaining wall is safe. Second case here is going to be sliding check in case of cantilever walls, and it is going to be the same procedure exactly as discussed in the gravity wall, except that in that case we will have an additional weight, which is the weight of the soil above the base slab, and this will contribute while calculating the friction force. Now we are going to check the overturning in case of gravity walls, and in this case the overturning moments are going to be due to the soil active force multiplied by the arm of the force, and the resisting moments shall be passive pressure behind the retaining wall multiplied by the arm of the force, in addition to the weight of the retaining wall multiplied by the arm, which is the horizontal distance between the wall centroid and the toe point. This is going to be very clear once we start solving our example. And the last case here is going to be check of overturning in case of cantilever walls. And again, it is going to be the same what we did in gravity walls, except that we are going to add the weight of the soil multiplied by the arm toe. So now, let's have a couple of examples on this. So let's check this example. We have a retaining wall with height of 12 feet. The backfilling soil density is 120 pounds per cubic foot. It is saturated 5 feet below the ground, and the angle of internal friction is 30, we want to calculate the overturning moment at the base of the wall per unit length. First step, always we'll calculate the coefficient of active pressure, which equals tan square 45 minus pi over 2, which is 30. So this will equal 0.33. After that, we will start drawing our pressure, which looks like this. We have the triangle till P1, which is at the top of the first layer before the water, and P2 at the bottom here, and of course we have the water pressure, PW. So let's start calculating each one. P1 will equal gamma multiplied by K by H, which is 120 multiplied by 0.33 multiplied by 5, which will equal 200 pound per square foot. P2 will equal P1 plus gamma KH, which is 200 plus 57.6, because this is submerged soil, so the effective gamma will be the 120 minus 62.4, which is 57.6, multiplied by 0.33 multiplied by 7, which equals 333 pound per square foot. P water equals gamma water multiplied by H, which equals 62.4 multiplied by 7, which equals 436 psf. Now we want to calculate the force due to each pressure. So F1 will equal 200 multiplied by 5 multiplied by 0.5, because this is a triangle shape. F2 will equal 200 multiplied by 7, which equals 1400, and F3 will equal 133 multiplied by 7 multiplied by 0.5, which will equal 465 pound, and F4 will equal 436 multiplied by 7 multiplied by 0.5, which will equal 1529 pound. So now we want to calculate the overturning moment, which means we will multiply each one of these forces by the arm. So this will be, as we can see here, 500 will be multiplied by 7 plus 5 over 3, because this triangle at the top here, the distance between the bottom and the centroid of this resultant force is the 7 feet, in addition to a third of this 5 feet height. So this will be 7 plus 5 over 3, in addition to 1400 multiplied by 7 over 2, because this is a rectangle shape, so the centroid or the resultant of the force will be at the center. So this will be 1400 multiplied by 7 over 2 plus 465 multiplied by 7 over 3 plus 1529 multiplied by 7 over 3. So the total overturning moment will be 13,880 pound foot. So let's check this example. We have a retaining wall as shown here. The height is 10 feet. The density of the soil is 125 pound cubic foot. And the angle of internal friction is 32. Gamma concrete is 150 pound cubic foot. And we want to calculate the factor of safety against sliding and overturning. We will start by calculating Ka, the coefficient of active pressure, which equals tan square 45 minus phi over 2, which is 32. So this will equal 0.31. So the soil active pressure behind this wall will look like this in this triangle. Let's calculate the value of P, and it will equal gamma multiplied by K multiplied by H, which will be 125 multiplied by 0.31 multiplied by 10, which will equal total of 384 psf. Now we want to calculate the force due to this pressure, which will be the area of this triangle. So it will be 384 multiplied by 10 multiplied by 0.5, which will equal 1920 pound. Now let's calculate the weight of this retaining wall or gravity wall, and it will equal to the area of this shape multiplied by the gamma of the concrete. Let's divide the retaining wall into rectangle and triangle. So the area of the rectangle, it will be 2 foot multiplied by 10 plus the area of the triangle, which is 0.5 multiplied by 10 multiplied by 6, all multiplied by the gamma of the concrete, which is 150. So this will be total of 7,500 pounds. The friction force equals the weight multiplied by tan, the angle of friction between the wall and the soil. We must take care now that we will not use the phi, which is 32, the angle of internal friction between the soil particles, but we want the angle of friction between the wall and the soil, which is given here as 20 in this problem. So this will be 7,500 multiplied by tan 20, which equals 2,729 pounds. So the factor of safety against sliding is 2,729 over 1,920, which will equal 1.42. So if we looked at the choices here, we can see that we have B and D already have the factor of safety for the sliding 1.4, so we can't directly choose, because for example maybe you can find only one answer with 1.4 as the factor of safety of sliding. In this case you will not have to calculate the factor of safety against overturning, and you can directly choose this answer, because you want to save time, of course, in the real exam. But here we have two choices with 1.4 as the answer for the factor of safety against sliding, so we must calculate the overturning also. So we will start by calculating the overturning moment, which equals the 1,920, which is F, multiplied by the arm, which is third height, which is 10 over 3. So this will equal 6,400 pound-foot. And let's calculate the stability moment, which equals the weight of the wall multiplied by the horizontal distance between the centroid of the wall and the toe. In this case, we will divide the wall into two shapes. Again, this triangle and the rectangle of 2 feet width and 10 feet height, and the triangle with height of 10 feet and base of 6 feet. And each one of these areas we will multiply by the distance between it and the toe point at point A here, as shown in this graph. So the stability moment will be 2 multiplied by 10 multiplied by 150, all multiplied by the distance, which is half the 2 feet plus the 6 feet of the triangle, so this will be 7 feet, plus 0.5 multiplied by 10 multiplied by 6 multiplied by 150, all multiplied by the distance of the centroid of this triangle, and it is at the third from the base direction, so it will be 4 feet. So calculating the stability moment, it will be 39,000 pound-feet. So the factor of safety is 39,000 pound-feet over 6,400, which will equal 6.1. So this is the answer, which is D, 1.4 for the factor of safety against sliding, and 6.1 for the factor of safety against overturning.